Hi guys, so today we're going to continue graphing rational functions. So what we're going to do today is look at a couple more complicated ones that have some components that we didn't see yesterday. So if you look at this very first function, just like yesterday, the first thing we're going to do is we're going to factor. Okay, so when I factor the top, that's a difference of squares. So the top of this function factors into x plus 2 times x minus 2. And then right from the start, you guys can see this is going to be a very different function than what we've had. Because what's going to happen here is those x minus 2 factors are actually going to cancel out. Now, anytime you cancel out a factor, you may have seen this in Algebra 2, this is going to create a removable discontinuity. Or an easier way to say that, it's going to create a hole in our graph. Alright, so anytime you have a factor that cancels out, the reason I'm calling it a removable discontinuity is because that's the terminology you'll hear in calculus when we talk about continuity. So this is a specific type of discontinuity in that it's called removable. So a removable discontinuity. And sometimes you'll see me abbreviate that RD, because I don't want to write all that out. But more commonly, you may hear that just referred to as a hole in your graph. So a removable discontinuity is a hole. So what happens when you cancel out a factor, we'll have basically an open circle on our graph, because it means our graph is going to be that entire function except for that one x value. And the x value is the 0 of the canceled out factor. So for example here, I crossed off x minus 2, which means the hole here, or the removable discontinuity, is going to have an x value of 2. Then to get the y value, I plug that x value in to the remaining equation. So I'm going to plug that into the remaining function. So I take 2. The only remaining function I have here in this case is x plus 2. So that's all that's left at this point. I plug 2 into that, and I get 4. So what that means is on my graph, whenever I draw this, I'm going to go ahead and plot that first. At 2, 4, I'm going to have an open circle, because that's basically the only point in my graph that's not going to exist. Now, if you were to graph this on a calculator, it'd be really hard to see unless you zoomed in pretty close to where this point is, and you'd see this little itty bitty gap. But basically, there's just a hole at your graph at this point. So now, what we would do at this point, once we've plotted our hole, we graph the remaining function however we need to. So my remaining function here, what's left after I find my hole, in this case, isn't actually even a rational function. It's just the equation y equals x plus 2, which is a straight line that goes a y-intercept of 2, a slope of 1, and we know it's going to go through the point where that hole is. So that's what my graph would look like at this point. So this doesn't even look like a rational function, it's just a line with a hole in it. Now we'll look at some where this actually could still be a rational function, but what's important here is anytime you get a factor that cancels out, it's going to create a removable discontinuity or a hole in your graph. Now we're going to go through and review in a little bit to kind of show the steps here, but this is the reason why it's very important to always factor at the very beginning. Because if you guys noticed, if you just looked at this very quickly, you may think this graph had a vertical asymptote at x equals 2, but it doesn't have a vertical asymptote because there's a hole there instead. So you always need to factor first, then look at whatever you have left over in your function. So let's look at another example that's going to have a hole in it. So this example here. Now this one's already factored for you, so it makes it a little bit faster, and you guys can see what's going to happen. So if you look at this example, the factor x minus 5 is going to cancel out top and bottom. By canceling that factor out, that means I'm going to have a hole in my graph. So this graph is going to have a hole, or a removable discontinuity. Remember, those are the same thing. The x-coordinate of that hole is going to be 5. because that is the 0 of the canceled out factor. Then to get the y value, I plug 5 into the remaining function. Now be careful here. The remaining function in this case is not x plus 2, because x plus 2 is still in the denominator. My remaining function is 1 over x plus 2. So I plug 5 in there, and I end up with 1 over 7. And that's where the whole of my graph is. Then at this point, I'm going to graph the remaining function, and my remaining function is still actually a rational function. So now I'm going to have a rational function with a hole in it. So I'm going to go ahead and graph the function y equals x plus 2. So I know that function is going to have a horizontal asymptote at y equals 0 because it's bottom heavy. I know it's going to have a vertical asymptote at x equals negative 2 because even after I cancel out that factor, there is still an equation in the bottom. I'm sorry, there is still a 0 at the bottom. So I'll plot my asymptotes first. So there's my vertical asymptote and my horizontal asymptote. I know this graph is not going to have any x-intercepts because the top can never equal 0. And I also know that the y-intercept, if I go ahead and plug that in, plug in 0 for x, I would get 0, 1/2. So that's my y-intercept. That helps me kind of see the shape of this graph. And then I know there's going to be a hole at 5, 1/7. So I'll go over to 5. And then it's kind of hard to show 1/7 cut so small, but I'll go ahead and at least put a circle there towards the bottom. And if you were to go through the whole process of your sign chart, you would notice this graph is negative on this side. It's positive, it goes through there, and it goes through the hole. So it looks just like the function y equals 1 over x plus 2, but the only difference is you have that hole in your graph because of the canceled out factor. Alright, so anytime you're dealing with a rational function, we always factor first. Then we're going to see if anything cancels out. So if a hole is there, we have to do that before we actually graph anything else. So we look at the remaining function then. Okay, the last thing I want to look at is if we get a case where we have no horizontal asymptote. So we talked about this a little bit in the previous lesson, where if the degree on top is higher, we know there's no horizontal asymptote. But if there's no horizontal asymptote, we have to check for a slant asymptote. So if the degree on top is exactly 1 degree higher than the degree in the bottom, then there's going to be a slant asymptote. Okay, so if the degree on top is 1 degree exactly higher, so if let's say I had x to the third plus 3x squared minus 2 over 7x squared plus 1, that's 1 degree higher, that would also have a slant asymptote. So if you end up with a slant asymptote, what you need to do in order to find that is actually use division. Now let's just double check and make sure there's not a hole here in this graph, because that's always a possibility. If you think about that very first example, it would have looked like there could have been a slant asymptote if I didn't factor first. So if I factor, I need two numbers that multiply to -5 that add up to a -4, which could be a -5 and a +1. So the top would factor into x minus 5 times x plus 1. Also, factoring makes it easier for us to find those x-intercepts later on. So nothing cancels out, so I'm going to check for that slant asymptote. So I'm going to do division. Now, if you're dividing by something like x squared or x cubed, you would have to use long division. But if you're dividing by just x plus or minus a number, we actually can use synthetic division to make this go a little bit faster. So I'm going to go ahead and do synthetic division. So 3 goes in the box, and my coefficients are 1, -4, and -5. What's nice about this, though, when it comes to finding your slant asymptote, the remainder doesn't matter. It's not going to make it as much of a difference on our graph as we really worry about, so we can ignore the remainder when it comes to this. So we're actually going to ignore that. The remaining function that I'm left with would just be y equals x minus 1. Now, I do want to review long division real quickly, just in case you do have a case where you have to divide by a higher degree polynomial. So if you don't remember the process, x divided by 3 is going to get divided into x squared minus 4x minus 5. And to find what number goes up at the top, all we're going to care about is the first term of both parts. So x times something gives me x squared, and that's x. Then I multiply x times both numbers on the left, so I get x squared minus 3x. Then I subtract both of those. So I'm doing negative 4 minus a negative 3x. That gives me a negative x. I bring down the minus 5, and I get minus 1. And again, at this point, the remainder doesn't matter. It's not going to affect my graph because we're not going to worry about graphing the remainder. We're just going to graph the slant asymptote, which is the line y equals x minus 1. All right, so let's go ahead and graph that slant asymptote. So I'll put that on there first. So y equals x minus 1 has a slope of 1, y-intercept of negative 1. So I know that is going to go through here, here, and it's going to look something like that. Then once you have your slant asymptote from this point, everything else we're going to follow is going to be the exact same steps that we've had. So I'm still going to find the vertical asymptote, the y-intercepts, the x. So let's find our vertical asymptote. And let me just list what we had. I had a slant asymptote of y equals x minus 1, and I found that using division. And again, I just want to stress this again, factor first. All right, if this graph had a hole, we wouldn't have a slant asymptote or even a rational function. Okay, we need to make sure that we factor this first and that nothing cancels out. Okay, vertical asymptote. After we've factored, we're left with x minus 3 at the bottom. So I have a vertical asymptote at x equals 3. So let me go ahead and graph that. There's my other asymptote. So you guys can see that where those quadrants are. It's very similar with that horizontal asymptote. It's just kind of tilted a little bit. I can find my x-intercepts. X-intercept is when the top equals 0. So this is going to cross the x-axis at 5, 0 and negative 1, 0. And then y-intercept, if I go and I plug in 0 for x, I would end up with negative 5 over negative 3, which would be 5/3. So let's go ahead and plot those points. I've got 5, 0. I've got negative 1, 0. And I've got 0, 5/3, which is almost 2. And just by looking at those dots, it kind of gives you a guide of what this graph is going to look like. If you want to do your sign chart, you can. But I know since I have to cross through these points and go towards my asymptotes, it makes it pretty clear what this is going to look like. And there's your graph. Just one thing to keep in mind here, remember, you cannot have both a horizontal asymptote and a slant asymptote. You will always have one or the other. Also, you may sometimes see a slant asymptote referred to as an oblique asymptote, just in case that comes up at some point, but more than likely we're going to refer to them as slant asymptotes. So the last thing I want to look at is just that chart that I gave you guys, so we can just kind of review everything we've looked at here. All right, now the goal for this is just kind of to sum everything up we've done these last 2 days and to give you guys something to follow as you try and graph these. So this includes both the parts we looked at today. So for the very top, it tells you a rational function, what it actually is, and it's a polynomial divided by another polynomial. Then we just go step by step in how we graph these. So step 1, we factor. All right, we factor. Always factor first because, again, you may not know that there's a hole in your graph or anything else along those lines. So we look for any factors that cancel out once we've factored. So we have to do this at the very beginning because it's going to change. It could change what you're graphing. So if a factor cancels out, it creates a removable discontinuity or a hole. And I'm not going to have a lot of space here because I need to write this big enough for you to be able to read. But that is a removable discontinuity or a hole. All right, the x-coordinate, to get the x-coordinate, that is the 0 of the canceled factor. And to get the y-coordinate, You plug 0 into the remaining function. I'm sorry, you plug the x coordinate, or the 0, they're the same thing. So you plug whatever you have for x into the remaining function. Don't plug it into the original, because then you'll get 0 over 0, and we'll talk about that later when we do limits. And then as soon as you've canceled out a factor, if you cancel out a factor, at that point, all you use for graphing is the remaining function. Okay, we're just using the remaining function. Now let's say you have something and you factor it and nothing cancels out. You just completely skip step 2, and we can just move on from there. All right, so step 3, we'll find the vertical asymptotes. To find the vertical asymptote, you set the bottom equal to 0. Then we find the horizontal asymptote. All right, so again, this is what we talked about the first day. If it's bottom heavy, if it's a bottom heavy degree, it's y equals 0. If they're equal to degree, we divide the leading coefficients. If it's top heavy, there's no horizontal asymptote. But this can be a case where there's a slant asymptote. And remember, this is top heavy after I've canceled everything out. So if I've canceled all my factors, if any do cancel out, and I still have a higher degree on the top by exactly 1 degree, then I'm going to have a slant asymptote. To find the slant asymptote, you divide. So I divide the top function by the bottom function. If you're dividing by x plus or minus a number, you could use synthetic, otherwise you'd have to use long division. And then you can ignore the remainder whenever you're trying to find the slant asymptote. The remainder is not going to affect it, so we don't need it. So we can ignore the remainder on that. Then the last 2 steps, we find our x-intercepts and y-intercepts. And if you remember from yesterday, the x-intercepts, we set the top of the fraction equal to 0, and then we plug in 0 for x to get the y-intercept. So that's kind of a little bit of review on rational functions and just looking at some new parts of them. We'll do some practice with that in class.